Okay, so dot product that we will proceed on. So we are talking about orthogonal component and dot product is kind of one of them. Okay, so what we have seen till now when we see the concept of dot product. So like we have taken the two vectors. So these are two vectors, and blue is A, and this one is black is A, and blue is B. A, B. Okay. Now the idea is to calculate A, A dot B. Theta is angle with it. So what we saw that if we want dot product of two vectors, then vector must be in the same direction. That is required. Once they are in same direction, then we multiply the magnitude of two vectors. So first idea is that to bring the two vectors in same direction. So this vector would come in same direction if we multiply this vector's magnitude with cos theta. Hypotenuse into cos theta. It will become base. So magnitude would reduce. If we reduce the magnitude, then vector would come in the same direction of other vector. If I say sine theta, then it will become orthogonal to it. Cos theta, it will come in the same direction. So B B cos theta into A. So B cos theta means B we reduced B into cos theta. Now they are in same direction, so we can multiply the magnitude. So A into B into cos theta. If that is the case, this is the one way we can calculate the dot product. What about calculating through orthogonal component? That is the idea. Means we have seen in the past that if we wanted to like in calculus, that if we wanted to do anything, then we have one thing that is graph equation. Like we want, I have, I have a, I have I have x vector, y vector, z vector. Now I have any surface, okay, x vector, y vector, z vector. Then I have one equation fxy. In that z equal to fxy function over x and y. Then there is another vector called u, x, y, u. If this is u, then what is dz by du? If that is we wanted, then we went for we went for local linearity equation. I believe we remember it. Local linearity equation. So in local linearity equation, we have fxy or gxy equal to fxxxy, okay, fxxy x plus fyxy y, or dz by dx x plus dz by dy y. So local linearity. Now x and y we can substitute with the, if there is a delta dz by du, if there is a delta u, if this is the u vector, then if there is a delta u along the u vector, then what is delta z? So if there are 2 points on this vector, okay. So if there are 2 points, okay. So if there are 2 points on this vector, and distance between these 2 points is delta z, then from one point we have z1, one point we have z2. Then, so the distance between 2 points is delta u. From one point there is z1, one point there is z2. Then what is delta z by delta u? This is what we wanted. That is, what is the differentiation of fxy along any vector u? So then we went for the local linearity and those. Then after that, one fellow that came for rescue was chain rule. That no need to go do that much. If you want dz by du, Then since it has component along x and y, so dz by dx into dx by du plus dz by dy into dy by du is also enough. If you have more dependency, then you can go for chain rule. Like u is also a function with t, then dz by dt equal to dz by dx, dx by du, du by dt plus dz by dy, dy by du, du by dt. You can keep going as a chain rule. Now we came as orthogonal component. So it is more advanced. So started with local linearity, gradient vector, and so many things, and then finally landed up in chain rule, and now it is orthogonal component. So orthogonal component. Now, if we are calculating dot product of two vectors, then a, if this is vector A, if this is vector A and B, then dot product of two vector is B cos A. Now they come in same direction and then multiplied by A. So this is the normal dot product equation. What about orthogonal component? Now the B vector. The B vector has B vector is set of three components. Okay, it has three components, B1, B2 and B3. So B1 is along x-axis, B2 is along y-axis and B3 is along z-axis. It is as good as three vectors were coming, one along x-axis called B1i, along y-axis B2j, along z-axis B3k. If all three vectors they combined at the origin and they came up to a new vector, then that is B. So B equal to B1i plus B2j plus B3k, or I can say it has three components, orthogonal components, B1, B2, B3 in direction of vectors I, j and k. Now question is arising, what is A dot B in the term of orthogonal component? Now B vector, suppose there is a vector along x-axis that is alpha I. So there is a vector called alpha I. Earlier we had vector called b1i. Now there is another vector called alpha I. So there are two vectors now. One vector is alpha I, another vector is b1i plus b2j plus b3k. Now, what is B dot alpha I? If so for the dot product, the grammar is two vector must be in the same direction. If they are in same direction, we can multiply the magnitude. That is the idea. Now B has three components. Now all three components we'll see how much they contribute in the I direction. Then we'll see what we have to do. So first B1. So B1 is already in I direction. So B1 into alpha. Both are in I direction. B2. B2, how much B2's component in I direction? So B2 cos theta in I. So cos theta is 90 degrees. Because B2 is in direction of Y axis. So B2 into alpha is nothing because cos theta is 0. B3 again Z axis. So along X axis it has no. That's why it is orthogonal component 0. So the B dot alpha I is B1 into alpha. B dot alpha I, two vector, if I do dot product, then B's only component, that is B1I, is along the Ix direction. If that is true, then B dot alpha I is B1 into alpha. Okay. Now what about B dot another vector that is called alpha I plus beta j plus gamma k? B dot another vector that is alpha I, beta j and gamma k. Now the another vector alpha I, beta j and gamma k, it is combination of again three vectors. It has three components, alpha, beta and gamma, in three orthogonal directions. But anyway, we'll start with the same fundamental. Now B's all component will see how much they contribute in I direction. B's all component they will see how much they contribute in J direction. And B's all component will see how much they contribute in K direction. So now all components only B1 contribute in I direction. Only B2 contribute in J direction. Only B3 contribute in K direction. So if I say B dot a vector that is alpha I plus beta j plus gamma k would be B1 alpha, one component, B2 beta one component, and B3 gamma as another, only three gamma. Other are all are 0. So B dot another vector alpha 1 alpha I plus beta j plus gamma k is B1 alpha I plus B2 beta j plus B3 gamma k. Plus is not required. I mean, these are the three components of the resultant vector or dot product. Generally, we say it is a scalar product. There is no vector that comes into the picture. So the three component of the dot product is like this: alpha B1 alpha plus B2 gamma B2 beta plus B3 gamma. If you want the magnitude, then you can do B1 into alpha square plus B2 into beta square plus B3 into gamma square root. So that is a Pythagoras theorem. Okay, so we have seen that much. Now, generally in mathematics, fundamentals do not work. Means we have to really prove it. That is the concept. Okay, so algebra is a science in mathematics that is generally used to prove the concept. Okay, so in this direction, on that direction will not at the end. Okay, so these are to make you understand, make things understand in kind of more realistic way. Now, if I want, now, okay, so probably I can do more on it what we have done. So I'll beat, we say B dot another vector that is alpha I plus beta j plus gamma k is B1 alpha, B2 beta and B3 gamma. Suppose the another vector is A. So B dot A equal to B1 A1, B2 A2 and B3 A3. Okay, so if I want dot product of two vectors, then their orthogonal components we have to do product and add it, or you can use the net magnitude, whatever. So these are the three components. Now we have to prove algebraically. That is the idea. Now there is a vector A and there is vector B. A dot B. Okay, that is A1I plus A2J plus B3K in braces. Inside braces, A1I plus A2J plus A3K dot in another brace B1I plus B2J plus B3K. So this is what we want. Now let's go with the multiplication. Now it will come as A1I dot B1I, okay, plus a1i dot b2j plus a, okay, a1i plus a1i into b1i plus a1i into b2j plus a1i into b3. I'm sorry, so I should not use multiplication, so let's use dot. Now we want a dot b, that is a1i plus a2j plus a3k dot b1i plus b2j plus b3k. That will come as a1i dot b1i plus a1i dot b2j plus a1i dot b3k. That is the first one. Okay, now as per the multiplication, now plus, now this is one component. Another component is a2i into b1i. Okay, a2 sorry a2j dot b1i, a2j dot b2j, a2j a2j dot b3k. This is another component. The third component is a3k dot b1j, a3k dot b2j, a3k dot b3k. Now in the first one, a1i dot b1i is okay. That is a1 into b1 because they are in same direction. Vector has to be in same direction for dot product. Next is a1i dot b2j. So ij are orthogonal to each other, so 0. a1i dot b3k, so 0. Like that, we will get lot of 0. at the end will come up as three component as A1I, A1 B1, A2 B2, and A3 B3. So three components, if we go for simple dot multiplication also, we'll get three components. A1. So what we need to do is that we need to just combine the three components. Okay, they multiply the three components individually and add it. So A1I, A1 B1, A2 B2, and A3 B3. Like we showed the three wires. Okay, so the way we showed that I think one wire is again missing. So it is like two components, green one we have to multiply, then two components, red one we have to multiply, and two components, okay, blue one. So blue is missing. So blue one we have to multiply. So that is the concept of uh, dot product. Okay, so where the dot product is actually it is useful. So that is the concept where dot product is useful. So suppose that I have a kind of okay. So this is yellow. Okay, and this is light. Now, if I if I do like this and place the light, it is glowing. We can see. Okay, or if I place like this, it is glowing. Now I am rotating the light. Can you see? Light is gone completely. Now I am rotating the light. Okay, it is falling here and it is maximum. Light gone. Light came, maximum shining. Light gone. So what it tells? So this surface has a normal. The surface, the surface has a normal. Okay. Suppose that when we place like this normal is y-axis. Okay. And when we glow the torch, light the torch, then certainly this is again y-axis. If both are in same direction, the normal y-axis and torch y-axis, the glow is maximum. But when we start shifting what we are doing actually. So there are two vectors. One is normal vector, that is y-axis, and another vector, that is y-axis. So A and B both are y-axis. Now if I rotate the torch in xy plane, then it becomes x. So if torch is like this, then it is y-axis. Now it is going towards x-axis and it becomes completely x. Okay. So the dot product of light direction and dot product of light direction and the normal vector is the light on the surface. Okay, so that is the dot product. If dot product of the normal, that is along y-axis, and dot product of the normal and the so dot product of normal vector and light vector, that so light, normal vector and light vector, whatever the dot product is, that is the light on the surface. So if light is in y direction and normal is in y direction, maximum light we are getting, because it is direct multiplication of their magnitude. But if once light is shifting, the cos theta we are getting. So if cos theta is 1 degree, 2 degree, 3 degree, we are getting. Okay. But if it crosses a limit, then that light cos theta become not is that much that we get the light, or we can have bigger one. So I have a kind of a plate. and then I can let it see the light on the plate. Okay, now light is shifting. Okay, light completely gone. If it is 90 degree, then if those vector at 90 degree, then light, see the light. Light is coming now. See, there is no light. But light is there, very little. Essence is there. Now, maximum. Okay, light is still there. Light is still there. Now there is no light. So, dot product of the normal out of the dot product of the normal and dot product of the normal vector and the light vector. So that is the actual light that is falling that the so like if it is yellow, okay, if the surface is yellow or yellow is not a color actually, so it is a red and green one and zero is blue. So the color of this, so that is orthogonal component. Someone would say it is yellow. I would say 1.1.0. So that is the color. So red and green one and then blue is 0. So that is yellow. So 1.1.0. Whatever the color of the light is, suppose it is white, then 1.1.1. So the final color that it would show is the multiplication of red factor, blue factor, and green factor. So since there is no green here, so it will not reflect the green color. So only red and green. So it will look like yellow. If I place blue light instead of white light, if I place blue light, then there is no red and green. And here there is no blue. It would appear black because red is 0, here red is something. Green is 0, but here green is something. So it will become 0. And here blue color comes where there is no blue here. So again 0. So the net color what we see is the multiplication of all the color. Multiplication of, please mind it. So the surface color is RGB, the light color is RGB. Net color is RGB into RGB cos theta dot. So R, if the color of the surface is C1, CA, and color of the light is CB, then CA dot CB. If CA is if CA is 110 and CB is 001, then each portion we multiply and we get 0 irrespective of anything. So it will appear black. Suppose the color of the light is 111, then it will be 110 dot 111 dot product. So if it is at 0 degree, then 1 into 1, so it would appear complete yellow. But if there is an angle, then the color, even though it would appear yellow only, but it will be dim. This is dot product. Now, can we think about cross product? That is the question. So now we talked with three analogy. Can you see? One is if you want dot product of two vectors. If I want dot product of two vectors, vector A and vector B, B cos theta, then B comes in direction of A, then multiplication of their magnitude. So B cos theta into A. So that is the magnitude of the dot product. This is one way we calculated. Another way we calculated that it has three orthogonal components. It has three orthogonal components. So all three orthogonal components in x direction, all three orthogonal components in y direction, all three orthogonal components in z direction. Okay, that contribute to the three orthogonal component of the net vector or net dot product. So we saw that if it is b1, b2, b3, then only b1 is in x direction, others are orthogonal. So whereas for the a, only a1 is in x direction, other are orthogonal. So B1 into A1, that is one component, B2 into A2, that is another component, and B3 into A3, that is another component. So if you want the magnitude of the dot product, that will come as B1 A1 square, B2 A2 square, B3 A3 square, square root. This is the second thing we calculate. Third thing we calculate, we went for algebraic dot product. A dot B equal to A1I plus B2J plus B3K dot A1I plus A2J plus A3K dot B1I plus B2J plus B3K. Then we went for blunt dot product, and we found that again it is A1 B1 A2 B2 A3 B2. Now, can we calculate cross product? Now I'll tell you what is the science behind cross product. Okay, if I want to calculate if it is vector A and if it is vector B, I want to calculate A cross B, then that is A, and then A cross B will work only when if two vectors are orthogonal to each other. A dot B will work only when if two vectors are in same direction. Then we multiply the magnitude. But cross product will work only when A and B are orthogonal to each other. Then we can multiply the magnitude. Dot product, both vector we have to bring in the same direction, then we multiply the magnitude. Cross product, we have to bring both vector orthogonal to each other, then we can multiply the magnitude. So now can we see the first concept was we brought in same direction and then we multiplied the magnitude. Now we have to bring orthogonal and then we multiply the magnitude. One way. Second way is all components should be orthogonal. Third, we will go with the cross product. Three way we discuss. So can you try it? I mean, it should not be very difficult. Okay, I believe that it is understood. It is too hot here. So to beat the heat, so what we have now. Okay, so to beat the heat, so we have papaya. Okay, so this is the concept to beat the heat. Okay, so we can try. Yummy. It's like a honey. Too good. Means why to buy so expensive honey? You can just have it.